So today we're doing Soft Earth Chalk Talk 7. Details don't matter. You'll notice the little parenthetic statement, when systems are close to critical. We've talked a little bit about concepts of universality before, right? And my layperson summary of universality is that there are quantitative macroscopic behaviors of given systems that are very insensitive to the microscopic details. One, not the only way, but one of the ways that universality arises often is in critical points and critical phenomena. So systems that might behave very differently from each other when they're far from their critical points, like, magnetization or relaxation of a glass or flowing grains or whatever, can somehow magically behave similarly to each other when they're in the vicinity of a critical point or a phase transition, right? So this is the Details Don't Matter lecture. Next week, there's a Details Do Matter lecture. That's the idea. Where I want to start then is our normal, I know you're tired of seeing it now, phase diagram, but every time I draw the water's phase diagram, I introduce a new thing, right? So here we are. We know that critical point right there. We've talked about it before. What I want to talk about with this critical point now that I'm going to bring up is that there are two key things I want to mention here. Is that at that critical point here, right, where water is simultaneously a gas and a liquid, and neither and both, it's that there are power law fluctuations in various quantities that you'd be interested in. Density, heat capacity, stuff like that, right? So there's no characteristic scale in the structure or the dynamics of this material in that critical point. The other thing then that I want to raise is the coexistence of phases, right? So in this critical point, associated with that power law stuff is that we have simultaneously liquid and gas existing together in that vicinity, right? So, but there's another thing that I want to talk about now, right? So we know this is the solid, this is the liquid, this is the gas, right? And remember that in the solid situation, we have nice, orderly, minimum energy configurations of atoms that are mostly static, but they jiggle a little bit, right? So they're jiggling, but the jiggling isn't enough to break their bonds and let them fly around. In the liquid state, we have disordered structure, right? The molecules are buzzing around all the time. They have higher energy, they jiggle more, and with that jiggling, they're able to slide past each other, right? But they're disorganized, right? So, and remember I told you that there's nothing encoded in the structure of a liquid that can tell you much about its dynamics, right? It's just reconfiguring this disordered state all the time. And over here in the gas state, it is also disordered, and the grains are also, or the particles are also buzzing around, but they have more energy, right? So the first thing that I want to talk about today to introduce ideas of details don't matter is thinking about this problem and random walks, right? So if you could track one of these molecules, gas, like an O2 molecule in the atmosphere, right? What would it do? Well, we can't observe it directly, right? But we can look at particles that are small, but they're large enough that when the random vibrations of the ambient environment kick them, they move, right? So one thing that you can do, classic experiment from Brown, you can imagine like a tiny piece of dust that's sitting there floating on the surface of a cup of water, right? And if you track that dust, so at time 0, it's sitting here in the center, right? And at some later time, you observe it here, 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 okay? So Now, the piece of dust is speeding up and slowing down. If you could zoom in all the way to some infinitesimal scale of time and space, it would appear actually to be moving smoothly and continuously. But if you kind of just stroboscopically image it at discrete intervals, it looks like the dust is appearing to jump around, right? And it is undergoing a random walk, right? And in this case, the random walk is happening because of fluctuations. We say that it's thermal fluctuations, and what we really mean is that it's the kinetic energy of the molecules, the bath in this system, which is like the water that the piece of dust is sitting in and on, that's kicking it, and it moves around as a consequence, okay? So, okay, random walks, I should say, arise very often in many body systems where there are collisions, right? So in this case, right, you have a bunch of water molecules that would vibrate around, and those vibrations, you could think of them that they might just be like billiard balls, that they get kicked and they go in a direction, but when they smack into another molecule, they bounce, and they smack into another molecule and they bounce, right? And so each molecule on its own could execute just these ballistic motions, but there's so many molecules that they're all banging into each other, and the net effect is, from all these collisions, is that the particle undergoes a random walk. So I want to sketch this out for us. So in this case, we've drawn it in 2 dimensions, right? So there's an x dimension and a y dimension. I want to consider random walks in time. And so for simplicity, I'm just going to consider the x dimension. So let's say that we keep track of the position of this grain of dust, right, as a function of time, but we're only going to measure its position in the x direction. So we'll either just take 1 dimension from a 2-dimensional random walk, or you could imagine a simpler 1-dimensional random walk system. But if you could track that, so, you know, it's going to do some erratic random path, right? Release another one, right? So now we'll track a different particle or the same particle at some point later in time. Do it again, right? So we just keep releasing random walkers, and each one goes up and down and up and down, and if it's truly random, the mean position doesn't change. But what you recognize is that the longer that you wait, the further the random walker can be from the origin, right? So if you think about it like me, I toss a coin and I take a step left, and then I toss a coin, and if it's tails, I take a step right. I toss a coin again, tails, and I just keep tossing the coin. We understand that because I'm just moving left or right randomly, that my mean position averaged over a long time isn't really going to change. But we also understand that I might happen to flip 10 heads in a row randomly, and if I do that, I could be 10 steps from the origin, which means that the more steps I take, the more likely at some instance in the future I'm further from the origin. I won't stay permanently that side of the origin, right? What I mean to say then is that the variance of my position grows. The mean does not change, but the variance, or how far my position could be from 0, grows, right? So we can release random walkers and release random walkers, do this over and over. The upshot is that you could draw an envelope, right, that basically brackets the width of the walks through time, right? So imagine you release 1 million random walkers and this just becomes a cloud, right? And what you would see is that if I want to call this, right, x is my position, I'll call x prime the standard deviation of my position, or if you like, x prime squared would be the variance of my position, right? And so this line is describing how the standard deviation of my position from the origin grows with time. And in a random walk, it grows as the square root of time, okay? This is a classic canonical result. And in fact, if we want to be more specific about it, we could say that it grows as the square root of time times a coefficient that we'll call d, which is the diffusivity, right? So diffusivity you can think of as like the rate constant in this process. So the universal part is that any random walk will have a standard deviation that grows like the square root of time. The system-specific part is that the rate constant in that random walk, d, depends on all the system-specific properties, right? So you can imagine a system with more energy that has a greater diffusion because the vibrations are greater, right? You can imagine that the dust particle is sitting in a fluid that is more sluggish, in which case it's going to be getting kicked, but its response to move through the fluid is going to be moving slower, right? So we have this result here, and just to give you an idea, if we're thinking about it in the context of a fluid, the diffusivity is something like the inverse of the viscosity, okay? This is another classic result. The physics for us don't really matter very much, and so I'm not going to get into it. But I just want you to understand, remember, many-body collisions, often because of the randomizing component of many-body collisions making a particle's path be randomized after collision, have the effect of producing random walks. Basically, random walks have a universal scaling and a system-specific coefficient, all right? So let's think about this, some macroscopic consequences of this, right? So we'll go back to 2D. And so instead of one random walker now, right, we'll say, okay, imagine that what I do is I carefully place a blob of red dye in the bottom of a cup. So the red dye is actually a bunch of tiny little particles, right? They're particles that are tiny enough that they're going to be moved around by this thermal kicks, this Brownian motion, right? And so when I put this blob of dye in here, what's going to happen is that all the little dye blobs that are in that are going to move around. They're going to get kicked around, right? And they're going to move randomly. They're too small for me to see, but what I see is the net effect. The net effect that I see is that at some time later, the blob has spread, right? And if I draw it at some time later after that, I see that the blob continues to spread, and at some time later, the blob continues to spread. Sorry. And if I draw these lines as lines that are equally spaced apart in time, then what you would see is that the spreading is fast in the beginning and the spreading is slowing down as a function of time because the spreading is happening like the square root of time, right? So this is what happens to the position of a bunch of random walkers, and if you want to think of it in a real physical system, you can think of it as the rate that the dye blob is spreading, right? The net effect of all these random walks is the blob is going to spread out. And so the radius, right? The radius of that blob is going to grow like the square root of diffusivity times time. Same thing. Simple, right? Now, what I want you to recognize next, in terms of thinking of this in the context of transport, is that if we have random motion in the presence of a gradient, then we get flux. Okay? What do I mean by that, right? So we have randomness plus a concentration gradient. And the example that I'll give, this is a pretty classic example, right? But imagine what we have is a box. And in this box, on one side, we have a gas. And imagine that we could track these gas particles, right? So here's what we do. At time 0, we remove the barrier, right? So every individual gas molecule in here, it has an equal probability to go right or left, right? Each one of them is just going to undergo its random walk, okay? However, every time a gas molecule happens to pass over this boundary that used to be there, we now will see that there's a molecule on the right side of the box that was not there before, right? So of course we know that if we let this play out over time, that eventually we're going to have an equal number of gas molecules in the box, right? They're just going to move around uniformly and fill space. What you recognize then is that the particles don't have a preferred direction to move, but if they're all crowded in one place and they're moving randomly, that is going to produce a net flux or transport away from places where the concentration is high and toward places where the concentration is low, right? And so when we have randomness, which results from many-body interactions, and we have a gradient, spatial change in concentration, we are going to affect transport from that, right? And so we can write that, actually. So if we call the concentration of the particles phi, in this case, right? And we'll call this the x direction, right? That the flux that we would measure across this boundary would just be proportional to the concentration gradient, and the constant of proportionality would be that diffusivity. The rate constant that is saying how fast or how vigorously the molecules are jiggling, right? So this is the concentration gradient right here. That's the diffusivity. Okay. So this is another very common transport equation. If anyone's taken elementary physics, you've seen this again and again. If you come from the other side of engineering or geoscience, you've probably seen this equation in specific instances and maybe don't know how generic it is, right? We see this in terms of heat. We see this in terms of concentration of stuff, right? We see this in terms of particles being transported. The reason I want you to understand why this flux equation from diffusion is so common, right? Why it could come up again and again and again is that, heat transport moving through a solid by conduction is very different from dust or pollen grains moving in a cup of water, right? They're very different systems. But the idea of universality and details don't matter is that in the end, you have situations of a bunch of random motions in a many-body system, and that will give rise to this transport equation, okay? So we have diffusion of heat, fluid, particles, etc., and they all basically follow that same equation. So that gives us an idea about why we might get some kind of universality in transport phenomena, right? So I haven't connected this yet to like landscape features or patterns. And so that's what I want to do now, because I want to explore some other interesting non-trivial consequences of this completely generic random motion plus something, right? So randomness plus concentration gradient, we get a non-trivial transport equation that's ubiquitous. If we take randomness plus other things, we get other interesting behavior, right? So a thing that I want to talk about for a minute is a phenomenon known as diffusion limited aggregation. And diffusion limited aggregation is basically we have diffusion plus what we might call attachment. So particles diffuse in a medium, but when they encounter a surface, they attach, okay? So a common experimental situation where people do this is we're looking down from above. Imagine you have like an aquarium, but we'll just make the aquarium thin in this dimension, right? So we call this a Healy-Shaw cell, right? But we have some aquarium here, and you put a charge across. So you put a solution in here. Let's fill this with water, put salt in it, right? And then what we do is we put like some kind of charge on one surface so that what will happen is that some molecule will diffuse around in here, but it's a solute, some dissolved species in the salt, but that when it encounters a charged surface, there's a chemical reaction and it precipitates and it becomes a solid, right? So we know that chemical precipitation happens everywhere. Usually, if you want to precipitate a chemical, you have to overcome some energy barrier. You can do that by a variety of ways. In this case, you do it with an electric charge, okay? So you release some solute molecule, it diffuses around, but when it hits this charged surface, it attaches, okay? So now we do it again. Release another one, it diffuses around, it doesn't do anything until it hits this surface and it attaches. Do it again. Okay, right? So we get the idea. We just keep releasing these random walkers and the random walkers will start attaching to the surface. But what will happen, right? So now sometime later, we have these surfaces that are growing. So now a new walker comes up, and when it attaches to the previous deposits, or when it finds the previous deposits, it attaches also, right? So play that out again and again and again, and what will happen is that eventually you're going to start growing interesting features. Right? So these particles are drifting and they're attaching, and that's all there is to it. But you realize that once you start growing something like this, a random walker that gets released in here is very likely to find itself trapped, right? And it's going to attach to here, and it's not going to be able to make it down to here, right? And so this thing will start to grow a little side branch, right? So the point is that all we've done is say that the particles are moving in a random walk, but when they encounter a surface, they attach. And what happens under that action is that the attachment creates a geometry. The geometry screens the system so that it blocks solute particles from accessing certain spaces. So once you start sticking out, you're more likely to have a particle get stuck to you. Then you're going to grow and stick out more, and you're more likely to get a particle stuck to you, and so on, right? So what in the beginning just looks like complete randomness turns into something that somehow looks directed, structured, even meaningful somehow, right? And when you look at this pattern, we call these things dendrites. You can grow these very easily doing the exact experiment that I've drawn here, right? So you can just have a dissolved salt and a charged surface, and you can grow dendrites from chemical precipitation. They also look a lot like certain kinds of corals that grow, and you can imagine why they might follow a similar growth rule. I should also say that this looks not unlike river channel networks, and it turns out that the equations that we have that describe the growth of river channel networks by erosion are sort of like a mirror image version of the equations that describe the growth of these dendrites by deposition, right? And so when you think about, random growth plus attachment, what I want you to understand then is that we can produce rather generic patterns that we see pop up over and over and over again. And this is an example of how in systems whose dynamics are governed by randomness, we tend to have this pull toward universality, right? Systems that are governed by randomness tend to have universal characteristics because randomness, as I said, is sort of a net effect of a lot of many-body interactions. Universality is behaviors or consequences that are not sensitive to the details of the system, right? So by definition, when we throw our hands up and say that the net movement of these molecules in this solute is a random walk, we're essentially saying we've given up caring about the details of what's going on, right? So this is randomness plus attachment. Now I want to talk about randomness plus connectivity, okay? And so here's the game that we're going to play now. Let's say that I have a little tank again, okay? This time, The tank is filled with water on the side, all right? And what we're going to do is say, I fill up a tank with water, and it's attached to a block. You can imagine this block as a rock, okay? So let's say that this is a block of impermeable material, right? We have a tank of water up against it, right? So of course, there's pressure here, the hydrostatic pressure. The hydrostatic pressure of the water creates a pressure gradient, right? The water wants to flow into this block, but the water cannot flow into this block in the beginning, we'll say, because this block is impermeable, okay? So now, just for the sake of simplicity, we're going to discretize this system, right? So we're going to imagine that we project a grid onto this block. And what we're going to do is this. We're going to say, okay, at time 0, I pick randomly one of these squares, okay? I landed right in the middle, interesting, right? But I'm going to pick that one, and I'm going to flip it from impermeable to permeable, right? And I ask the question, does any flow come out the other side? Can you guys give me an answer? Thumbs down, no, right? I've somehow flipped this part in the middle and made it permeable, but there's no way for the water to get there, right? So now I do it again, all right? This one, I'll do it again, this one, right? And so what I realize is I have a constant pressure gradient applied here, and what I want to measure is the flow or the flux of water that's coming out. And what I realize if I'm making a graph of this, I'm going to make this the percent of the block that is porous, right? And I'm going to make this the flow out. So I made it, let's say, 2% porous, 4% porous, 8% porous. And what you realize is that so far, nothing, right? No flow. So I flip another block, I flip another block, I flip another block, and you can see how this is going to go, right? And eventually, I flip enough blocks that there is a path. That there's a continuous path. Well, I didn't fill these in, but you know what I mean. There's a continuous path of permeable blocks from the left to the right. And now, all of a sudden, flow can commence. So what I would see is that I do that experiment once, and there's no flow, no flow, no flow until I have a connected path, and then it jumps to some high flow rate. If I keep turning blocks after that, I could presumably keep increasing the flow rate because I'm just making like the channel wider, right? Okay. So if I do that once, I get some graph that looks like this. I'll do it again. Start the experiment over, do it again, and maybe I have to flip more blocks because it's random, right? Maybe I do the experiment again and I flip fewer blocks. So now I do the experiment a million gazillion times and I average the crap out of it, right? And if I do that, then what I get is some curve that looks like this, right? This curve says, okay, if I start with an impermeable block and I'm applying a pressure gradient across it, there's no flow, no flow, no flow, and then at some point, I gradually pick up the flow, right? And when you look at this curve, you look at this hinge point in the middle, and I would say that is a critical point, right? This is a system that has a critical point. There's a state of no flow over here. There's a state of saturated flow over here. And there is a nonlinear regime where we go from a state of no flow to a state of flow, right? And in this regime, right, we have mixed phases. in this regime, by the way, we have power law behaviors that we could talk about. But what I want you to know is that this problem is a problem called percolation, and it's called that because it comes originally from thinking about flow through porous media, percolating through porous media. However, it arises anytime there is a problem that involves randomness and connectivity, right? So here, we have this situation where I can flip the coin and I always have this abrupt transition, but if I average it like crazy, I get this continuous transition here, right? So this problem of percolation is a problem that we encounter associated with state transitions in real systems that we care about. And I want to give you a couple examples that will make it hopefully a little more visceral and a little more real. And the first example that I want to give you is thinking about flow through a pipe, okay? So the idea is now that we're going to impose some fluid flux into one end of the pipe, right? And of course, in our closed pipe, the mass is conserved, so whatever goes in has to come out. But what we're going to do is sit here as an observer, and we're going to measure at one point the instantaneous velocity in the pipe. And I like to do things just in one dimension. So we're just going to look at the downstream velocity, right? So we have to introduce a dimensionless number that some of you might have heard of, some of you might not, but it's going to become important in a second, and it's the Reynolds number, okay? So when we think about flow, we have to consider the Reynolds number if we want to understand the state of flow inside this pipe. Okay, so Reynolds number, this is density of the fluid, this is velocity U, L is a characteristic scale, like our pipe diameter, and then mu is the fluid viscosity, right? And the reason that we have to introduce this is that the Reynolds number is a ratio of inertia to viscosity. And the way that I like to talk about this is, it's not exactly related, but maybe you had experience with it. If you're driving and you encounter a traffic circle or a roundabout, whatever you call them in your part of the world, right? So you encounter this traffic circle, and this is what you want to do, right? You want to get to the other side. So you want to come up to the traffic circle, you want to hug that bend, and you want to keep control of your car, and you want to come out the other side and keep going the way you're going, right? And what you understand is that if you're driving slowly and your inertia is small, that you come around this curve no problem and you continue on your way. But what you understand is that if you are approaching this curve too fast, right? So you can turn to make yourself around, but you try to turn back. And the problem is that your car has a lot of inertia and it wants to keep going in the direction you turn the wheel, right? And that can send you skidding out uncontrollably, right? It's kind of similar now with the situation in the pipe. So we have this flow in the pipe, and we want to ask, if I disturb that flow somehow, can the flow recover? Or does it have so much inertia that a disturbance that I've introduced into the flow is actually going to cause the flow to spiral out of control, right? So the idea here is in the flow in the pipe, first, we'll look at the velocity of our observer here and our sensor there. So we'll look at the velocity as a function of time for a situation where the Reynolds number is small, less than 1, right? And if I do that, it's a very boring plot. So I have a constant discharge in, I have a constant diameter pipe, so I should have a constant velocity. And indeed, if I measure that velocity, I just see it as a flat line doing nothing interesting, right? This, by the way, is what we call the laminar regime, right? So now I consider a situation where I crank the flow rate up. I crank the flow rate up, so I crank the speed up. And I now have a Reynolds number that is big, much greater than 1. Let's just say 100, 1,000, 10,000 if you want, right? If I look at a time series of the flow velocity that I'm measuring at one point in there, what I now see is something that looks like a random walk. Okay? So, if I have a constant flow rate in, I have a constant flow rate out, the average velocity should be fixed and determined by conservation of mass. But I have a lot of fluctuations around that, right? A lot of fluctuations. And this is the regime, right, that we call turbulent, okay? So there is a state transition in the flow where it goes from nice and orderly and where it heals from perturbations, that's laminar flow, to a situation where the flow is unconditionally unstable, where all disturbances that you put in it grow, and where the dynamics are chaotic. This is a state transition. And so it hints that there's a critical point somewhere, right? That is what we're after. So in relation to what we talked about before in terms of recovering from disturbances, here's our laminar flow case. In the laminar flow case, we put an obstacle, right? So it's just like the traffic circle. If we put a blob of dye and we let it make a streak, this is what happens, right? In the low Reynolds number regime, the flow goes around the obstacle and it recovers, okay? So if we're in the turbulent regime here, and we do the same thing. So now let me do it a little upstream. So we introduce an obstacle there. So flow comes around. And it does not recover. Right? So these little whirling, swirling things I did is supposed to be showing you that in the beginning, the flow tries to go around this obstacle and it can't turn back in response to the pressure gradient on the other end. It induces a rotational motion, right? That rotational motion is what we call eddies, and these eddies grow, right? And so what you see happening downstream is this disturbed region grows, and the disturbed region grows until it occupies the entire diameter of the pipe, and at that point the flow is completely turbulent, okay? So where is the critical point in all this, you might be wondering? Well, there are a few different ways that you could draw it, but what I want to point out here is that in this diagram that I've just drawn, within this red part, the flow is turbulent, and outside of that red part, the flow is laminar. And so what you recognize is that we've made a spatial transition from laminar to turbulent, right? And what you can see is that the laminar and turbulent phases are coexisting together. Turns out there's a razor-sharp boundary. The flow is either totally ordered locally or completely disordered locally, okay? It's almost like a coexisting solid and liquid phase together, right? It's weird. So one diagram that we can make, right? So I can characterize these deviations of the velocity from the mean with u prime, just like we talked about the deviations from the position x as x prime, right? So I can describe the standard deviation, how much variability there is in the flow velocity with the u prime parameter, right? And so what I'm going to do in this plot is it's going to be the Reynolds number on the x-axis, right? And it's going to be measuring the magnitude or the variance. We're going to measure the variance of the velocity, right? The magnitude of the velocity fluctuations on this axis. So you already have an expectation, right? You know that when the Reynolds number is less than 1, based on what I drew here, that this is going to be small, right? There is a tiny bit of variation because of molecular diffusion, but it's pretty small. So this isn't going to vary very much, right? You also know, because I told you, that when the Reynolds number is really big, let's just say 1,000, right? That somewhere over here, that the variation in velocity is big, right? It's turbulent. It's behaving like this, very erratically. So if you measure the variance of the velocity as a function of the Reynolds number as just one way to characterize this transition, what you see is this classic sigmoidal type curve, the kind of curve that we tend to see in percolation, right? What's happening here in this situation is that it's subtle, but as I drive the system at higher energy, I kick off little puffs of turbulent regions. But if they're isolated from each other, the flow is still pretty much laminar with just a few little puffs in it. It's kind of like when this thing is a solid block with just a few isolated impermeable blocks in it, right? But what happens is that as those puffs grow in their size and their stability, they link up with each other. The net thing that we call turbulence, when we have a wholly turbulent flow in the bulk, it's because a bunch of little turbulent puffs have actually linked together to percolate across the system, okay? And so what we actually see, so sure enough, if you look at the velocity fluctuations, I'm only plotting the variance, but if you looked at the full probability distribution, what would you see? You'd see power law fluctuations in the velocity, and what you would also see, coexistence of phases, right? The critical point here is characterized by the velocity fluctuations going from being well-bounded and small to being power law, scale-free, and big, and we go from having one phase to a mixed phase, right? And so this is a critical point, and in fact, the transition from laminar to turbulent flow is in the percolation class of transitions, right? So it's the very same transition, and that means that we can even see the same scaling and the same math that we see in this permeable-impermeable percolation transition problem, right? It's pretty cool, I think. Let's think about another system. Let's go to an extreme now. This was pure fluid. Let's think of one that's pure solid, okay? So in our pure solid system, here's what we're going to do. We're going to squeeze a rock, okay? So we have an experimental system here. We put a rock in the middle, and all that we're doing, we're compressing it from the top and the bottom. So this is a compression test, but if it's a uniaxial test, you also get shear, of course, because what happens when you squeeze it this way is that the rock goes this way, right? So we start out with a piece of solid rock, and we squeeze it, right? So we know that if we plot the stress and the strain, right? So the strain is the total amount of deformation, right? We know that if this thing is behaving like the simplest solid we know of, it has this elastic response. Then as we start to squeeze the rock and we increase the strain or the total amount of, the relative amount of deformation, that the stress goes up linearly, right? This is the portion where it's behaving like a spring. But at some point, a crack nucleates somewhere, right? And it starts to grow. And another one nucleates somewhere and starts to grow. And another one nucleates somewhere and starts to grow. And in the beginning, these cracks are growing, and so they're dissipating energy. And so you start to see this linear relation roll over a little bit. It starts to get some curvature. The cracks grow, and at some point, a system-spanning crack percolates across the rock, and the rock flies apart, right? So you're gradually loading the rock, but the rock is a solid until all of a sudden it's not, right? And so what happens in that regime, right? So we know that this is the yield stress, right? What you see happening, though, in this portion of the curve is a percolation transition, right? So the cracks are growing, and when the cracks are growing, you have this mixed phase thing where you have portions of the rock that are competent and undissected, and you have portions of the rock that have cracks growing within them. And when the cracks percolate across the sample, then the sample fails. And you see that the macroscopic response of that, right, in the stress state, right? And so this is yet another example of randomness and conductivity. But in this case, right, it's randomness because cracks nucleating and developing in a solid material is known to be a strongly random process. That's at the heart of things like Griffith fracture theory, by the way, is that there's some random distribution of flaws inherent in any given material, and those flaws are the nucleation sites for cracks that grow. Right? By the way, since I know that this is a soft earth thing, and I have only talked about fluid and pure solid and not soft stuff, if we take a system of soft particles like just sand, right? Let's say that we have a box of sand and we're just shearing that box of sand. What we know is that when we shear it gradually, that we have a little localized region that rearranges here. Remember, we talked about that. And we have another one over here, and then another one over here. But if we keep deforming it, right, you all know where this is going to go. At some point, if we keep deforming it, there's a region where all of these localized zones of rearrangement link up. And now you have a situation where there's an interconnected chain of zones that are rearranging simultaneously. This is when the granular material will lose its competence and fail and flow. Okay? So this is also true in granular materials like sand and clay and stuff like that, right? So it's pretty generic. And the points that I want us to understand, right, when systems are close to critical, is that we have this coexistence of phases. We have these power law fluctuations. These are the hallmarks of this critical phenomena, and they're universal because these dynamics are very generic, right? These are just problems that are dominated by randomness and conductivity, and that the mechanical properties are related to randomness and conductivity. So let us talk about other mechanical changes that happen around these critical points and why they might be rather general or universal. Okay. So we're going to look at suspensions now. So these are particles for us that are sitting in liquid. I mean, they don't have to be in liquid. They could be in gas, but we're going to do liquids because it's simpler. So the idea here is that we have an experiment. Looks a lot better in my digital notes, okay? But we have an experiment. We call this a rheometer. It measures the flow of stuff, right? And basically, I like to describe it as like Imagine you have a stick blender and you put the stick blender into a bath of liquid, but you can change the attachments on the stick blender, right? So instead of making it a blade, we're going to make it a disc that just goes down on top, okay? So then that disc rotates. And inside here, we put our fluid, right? So we can put a fluid inside, and then you could spin this disc, and you can spin it at a prescribed speed, and you can just ask the question, right? If I'm spinning it at a prescribed speed, then I'm creating a shear stress between the plate and the liquid that it's in contact with. So I can say how much resistance to flow is there when I spin this thing, right? So this is a way that we measure viscosity, for example, of fluids. What we're going to do is consider a few different states of the system, right? So here we'll say that let's consider a case of pure fluid, no particles in it. We'll call the volume fraction of particles phi. So when phi is 0, there's no volume taken up by particles. It's all the liquid, right? Next to it, we'll have a dilute suspension, right? So you can imagine that you put some particles now, a couple percent, 5% particles, right? So you realize that if I'm whipping this thing around and the flow's moving around, that there's particles moving around in it, but they're pretty dilute. So even here, the particles are whipping around with the fluid, but they're probably not interacting with each other, right? They're not very likely to get close to each other, let alone collide with each other. There are not very many of them. You probably see where I'm going. If we make the concentration higher, you imagine that as these particles are whipping around with the fluid, that they might start finding each other more, right? They might bang into each other and dissipate some energy that way. Or just as the particle has to push fluid out of the way, the fluid it pushes out of the way might push another particle. So the particles could interact with each other by collision. They could also interact with each other through the fluid that they have to push out of the way, okay? So at some point when we add particles, they get concentrated enough, they're going to start interacting with each other. When they're dense but not too dense, their interactions are going to be principally hydrodynamic. They're going to be through the fluid. But at some point, let's say 0.6. We'll see why we'll come back to why that one. At some point, you add particles at a high enough concentration, and now you essentially guarantee that they're touching each other, right? So you can imagine a situation where you make the concentration of particles so high that the system becomes jammed. And it becomes jammed because you've packed so many particles into there that in order for one particle to move, it has to move other particles out of the way. But in order for them to move, they have to move other particles out of the way. And there's no room for any particles to get out of the way. And what's going to happen there then is the whole motion in the system will become arrested, right? So if you keep increasing the concentration to the point that the particles are just geometrically frustrated, they just can't move around each other at all, that is a volume fraction at which the system is jammed. And when it's jammed, it's now a solid, right? And in fact, if you keep stressing it, what's going to happen is it's going to crack. Rather than have it flow like a fluid, if you get it to the point that it's jammed, if the individual grains can't move out of the way, then they slide en masse past each other. Okay, so what's the critical point here? So what we can do is we can plot the viscosity, and it covers a lot of orders of magnitude, so we'll make it log. We can plot the log of viscosity against the volume fraction. So in the beginning, when we start, this mu0, this will be the viscosity of the carrier fluid. Let's say that we're doing water, right? So we know that when we start adding particles that the suspension starts from having a viscosity that is viscosity of water. And in the beginning, when we're adding particles, what happens actually is things are pretty simple. Einstein figured this out in 1905. It's a less famous paper than his other famous papers from that year. But basically, when you start adding particles, but they're in the very dilute regime, they increase the viscosity, but it only goes linearly with concentration. basically there's a drag penalty. There's loss associated with the drag around each particle, but you can basically just sum up the drag around every individual particle, and that just becomes like an added viscosity. So when the particles are dilute and not interacting with each other, the viscosity increases with phi, but it does so linearly in a way that is simple. Okay. What begins to happen, right? So this is the simple linear regime that's associated with a dilute suspension. The particles start interacting with each other in some interesting way in here, right? So this is the regime that's sort of like medium. In this regime now, the particles are not really colliding with each other, but they become concentrated enough that the little wake or disturbance regime of fluid around this particle and this particle interact with each other, right? So things get complicated. You can't just add up the drag around each particle anymore because the little wakes of the fluid around each particle start interacting with each other. Stuff gets weird. Then there's this regime over here, the jammed regime. This is the part I was saying where when the concentration gets high enough, at some point, at some critical packing fraction, the particles are so tightly packed that the material is jammed. What we're saying with this line is that the way to describe that is that the viscosity diverges. It goes towards infinity, right? So we can describe that, and what we can describe it as is we would say, okay, I'm going to take the viscosity normalized by mu zero, the viscosity of the carrier fluid. And what I describe in this situation, we can describe as something like this, right? This divergence quantity that says that the viscosity relative to the viscosity of the carrier fluid goes like phi c minus phi. So we call this the distance from jamming, right? Of course, if we're at jamming, you can check that this thing goes to infinity, right? So this equation says for sure, right, that what's happening as we approach this critical or jammed packing fraction is the viscosity blows up toward infinity. And it turns out that that exponent n, we don't really have a good theory for it, but it's pretty robust. It's about 2. So this is true for particles in fluids. All kinds of particles in all kinds of fluids, okay? And what's happening here is it's a critical point, right? It's a critical point where there's a quantity that's growing, diverging like a power law. And what's happening in this intermediate regime as I approach the jammed state, we actually know this from experiments, is I have locally jammed regions that are already behaving as little islands of solids, mixed with regions that are not jammed, right? So we have power laws, divergences, mixed phases, all the kind of stuff, right? And a very generic response. So when you look at this, it might remind you of something. It's okay if it doesn't, but it might remind you of something that we talked about earlier. Think in lecture 4. Does anybody remember when we talked about glass viscosity and temperature, right? So with glass, right, so we have temperature and we have viscosity. And what we know, remember, is that glasses, disordered amorphous solids, when you start out as a liquid and you cool them, that they don't have that big jump in viscosity like crystal forming materials do, right? They have no latent heat. And what happens is when you take the glass and you cool it, the viscosity is increasing as it gets cooler, but then there's a regime where it starts to blow up, right? And we described that. This glass transition says that there's some glass temperature. We usually can't measure the viscosity once it's reached that glass temperature. It's too slow, right? So what we do is we fit some form to it. But what we say is that we take the data that we have and we extrapolate it. We say there's some temperature at which the viscosity becomes infinite. And the transition to that is sharp but continuous, right? And that what we're seeing is a power law divergence in the viscosity on approach to a critical point, right? This glass version is like the mirror version of the suspension with packing fraction, right? So in glass, temperature is the control. In our suspension, the volume fraction is the control. But in both cases, we have this sharp but continuous transition from a fluid to a solid-like state, and they turn out to be intimately related, right? By the way, just to complete the story, is we can do this in terms of stress and viscosity for different materials. So if this is glass over here, if we look at the stress viscosity curves for things like grains or gels, what we also see as we approach from above is that we can think about the transition from the fluid state to the solid state, right, as we decrease stress from above. And here, this transition is the yield stress that we've already been talking about, right? So we have these sharp but continuous transitions from fluid to solid in all of these different disordered systems, but the driving parameter is different in these different systems, right? It can be stress, it can be volume fraction, it can be temperature. And so this has actually been put all together. I don't have enough time to go into it, but I'd be remiss if I didn't bring it up at all. This has been brought together, I would say conceptually, certainly, and maybe that this serves as a guiding framework, if not a theory, for further unification of these ideas into what's called the jamming phase diagram. And the jamming phase diagram, really what we're talking about is the transition from flowing to not flowing for all the disordered materials, for all the ones that exhibit this continuous transition associated with power laws and mixed phases and all that kind of stuff. And the axes on this jamming phase diagram, so we have temperature, we have 1 over the packing fraction, or if it's a glass, packing fraction isn't really relevant. We just say 1 over the density. So as you go out this way, we have to make it 1 over so that the axes work. And stress on this axis, right? And the premise now is that we can draw phase boundaries between flowing and not flowing for these different systems, okay? So over here, in terms of density and temperature, this would be the regime of glass, right? And inside of this envelope, you are jammed or solid, right? And outside of it, you are flowing, right? In this space down here, right? Jammed and flowing, materials that we might have there, right? So this is in the space of stress and volume fraction. So this is where things like granular materials and suspensions live, right? Along that axis, okay? And this doesn't mean that we have a unified theory yet, just because we have like a nice diagram with proposed boundaries. But there's this recognition that there's similarity in the dynamics that suggests pretty strongly that there's something universal about the way in which disordered materials undergo state transitions from flowing to not flowing. And this conceptual phase diagram has been a motivation for a lot of us to go around and collect data to kind of test and anchor and decorate this at the least, and also to drive the development of theory. So in the little bit of time that I have left, we're almost done. I just want to summarize And really, maybe I didn't, it's not summarizing, that's not fair, because I didn't really tell you how this is relevant for the soft Earth directly. So what I want to do now is just make a connection of these ideas to soft Earth problems, okay? And so the first point that I want to make explicit, if I hadn't made it explicit so far, is that sand pile creeps like glass. Okay, that's a glass that I drew there, if you can't tell, right? And so sand piles creep like glass. I don't just mean metaphorically. I've talked about creeping sand piles before. I mean when we measure the way that they relax, the way in which they strain harden, when we measure the configurations and structure of the rearrangements, what we find is that the sand pile relaxing under gravitational stress is dynamically just like glass under cooling. This is fascinating and vexing, but it's helpful because it provides, I would say, maybe the first open path for understanding and examining soil creep, right? So before we had this realization that sand creeps like glass, there were all kinds of crazy explanations for why soil outside on the hillsides creeps below the yield stress. And now we understand at least that everything that we've learned about creep in glass could be used, not exactly, but could be used as a model that we could test and figure out if it's somehow correct for explaining soil creep, right? So I'm very excited about the connections between glassy dynamics and granular dynamics because we're starting to have an emerging understanding of the sub-yield creeping behavior for these granular systems that we didn't have before. And I'll remind you what we talked about a little bit is that, like, I think it was lecture 4, that mechanical noise in a granular system might play a role similar to like what the thermal noise does in a glass system, right? One thing that I'm only gonna tell you at the end, what I mean is that I could have used this example, but I just wanna summarize some concepts with a new but relevant, beautiful example. As we move from the creepy to the catastrophic, if we consider debris flows now. So debris flows, I talked about a little bit. This is when thin layers of soil on steep hillsides suddenly fluidize, that you add water to them, they lose their rigidity, they unjam, and they flow, right? So there's two things about this, right? The important one for us, though, is that these debris flows are mixed phase systems. So they're made of soil, which of course has water in it in order to fluidize and make it flow. It also has sand in it. And it also has fine-grained particles. So we'll say, which is clay, which is sticky. And I'll label the sand, which we'll say is frictional. So these debris flows are a mixture of water, frictional sand, and sticky clay. Remember, I talked about the difference between purely frictional and cohesive systems, right? There's a quantitative and qualitative difference, right? Cohesive systems can withstand yield stress and all this kind of stuff. So what we know now is that the rheology of debris flows is controlled. Oh, I erased it. I erased the suspension one. It's controlled by the distance from jamming. What I mean is that we can demonstrate that the viscosity of real complicated mixtures actually follows the same divergence that we saw for idealized suspensions. But phi here is a material-dependent quantity. So particles that are rough will jam at a different packing fraction from particles that are smooth. We're going to talk about this next lecture, whether they're sticky or not sticky or anything else. But the other thing that we've demonstrated is that the second component of this rheology, if we want to understand the flow behavior of debris flows, is that debris flows in nature contain varying degrees of frictional and sticky stuff. It turns out that you can understand the transition from a frictional dominated debris flow to a cohesion dominated debris flow as a percolation transition, because it is. What do I mean by that? I mean, when you have a suspension that is predominantly cohesive, say, and then you start adding frictional particles. In the beginning, the frictional particles are not touching each other, and they're not doing very much, but at a critical density of frictional particles, they can link up or percolate across the system. And now, in order to move this debris flow, you have to overcome frictional resistance from these grains, right? And so there is a transition in the mechanical behavior of debris flows from ones that are cohesive to ones that are frictional. And that transition is a percolation transition, right? Again, we have randomness and conductivity driving mechanical changes in these systems, okay? So this is jamming, this is percolation, and it turns out that jamming plus percolation can explain a lot of soft Earth systems, okay? There's a lot of explanatory power in that. And a last example that I want to give to pull some of these things together is related to landslides. Landslides are like debris flows in some ways, but they're different in others, and I talked about that a little bit, right? So if we imagine that we have our nice hillside like this, right? So the landslide is a cohesive patch of material that detaches and flows. And basically, what I want us to take away is pulling together the volume fraction control and the stress control, okay? So we know that there's a critical volume fraction that if we're above that, there's not enough water in here to fluidize the grains, right? And that this critical packing fraction you could think of, if you have soil and you're wetting it, you could think of this as saturation, right? So I have a soil that's sitting there happily, and then I wet it, and I wet it, and I wet it, and at some point I add so much water that it pushes the grains apart and they lose frictional contact, right? So we know that there's a critical volume fraction below which the grains don't have frictional contact with each other, right? And so this is our usual jamming packing fraction, right? But we also know, right, that there's another confounding variable, which is stress, right? So we know that we can have a granular material not change its volume fraction and just push on it and push on it and push on it until it fails, right? So we know that there's some critical stress at which the material is going to fail and flow, right? And so it turns out that the envelope between flowing and not flowing for something like a landslide looks like this, right? So there is a packing fraction where if you're below that packing fraction, no matter what, even if there's no stress, you're going to flow, right? Because the grains are just not touching. There's nothing to stop flowing from happening. On the other end, there's a packing fraction that is so dense, the grains are so tightly packed together that no matter how hard you stress on it, you cannot flow, right? So this is the always flowing regime. This is the totally jammed regime. But in between those two packing fractions is this regime where whether or not you are flowing or not flowing depends on the stress, right? And so I bring this up in the context of landslides because two things happen. So when I rain on soil, one thing that happens is that I have grains that were sitting in air, and they now get saturated in water, and so there's a buoyancy force change, right? So essentially, the stress that's loading the frictional contacts goes down because the grains are now not as heavy relative to the fluid, right? I've taken air, I've replaced it with water. The grains are thousands of times heavier than air. They're only twice as heavy as water. So one thing that happens when I rain on soil is I just decrease the stress. So I can excite a landslide without changing volume fraction just by filling the pore space with water and changing the stress state. But the other thing that I can do, right, is I can change the volume fraction, right? So progressive wetting, right? As the fluid seeps into the soil, we have this progressive wetting, and when it fills all the soil space, if we keep adding water, it starts to push the grains apart and just force a change in the volume fraction, right? And so when I rain on soil, there are different paths. Presumably, it's actually something like this, right? It's some combination of both changing the stress that is activating friction and directly changing the volume fraction of the grains themselves that drives the system from a state of no flow to a state of flow. As far as we know, this framework, which comes entirely from looking at like soft materials, has not been applied to understanding landslide failure, but we think it's a promising avenue. So thanks for your attention. I'll stop there.
Okay, so there's these three things you were talking about: stress, temperature, and like
volume fraction. Yeah.
That are, well, from what I understand, the driving forces of these particular regimes, where the viscosity goes to infinity.
Yeah.
And so, what is it about those three things that makes them similar to do the same thing?
Yeah.
Like what is the similarity between them that cause them to make materials have the same effect?
Yeah. And just to make it weirder. So since we're talking about, earth materials, and I'm scared of like electricity and magnetism, that I don't talk about that topic very much. But, there are similar properties if you look at magnetization and temperature in a variety of materials where you'll see, how the magnetism changes with temperature, and you'll actually see like the same thing. Okay, in the glass is hard, but it's kind of the easiest to understand, only in the sense that in glass, we know that we have molecules that are bonded together, and we know that they vibrate, and we know that then we can say that there's an energy landscape, right? And we know that that energy landscape, we can put some constraints on what it looks like. So particles, like in the glass, the molecules are arranged in a haphazard fashion. They have bonds between them, but the bonds are stretched or compressed depending on their connection to their neighbors. And so there's this range of strengths of interconnectedness of the bonds. And then the good thing is we know what the distribution of thermal fluctuations is, right? So we know that temperature is our like mean description, but we know that we can describe the vibrational energies at a given temperature. There's a distribution of vibrational energies. And basically the upshot of that is that every once in a while we can figure out statistically how likely we are to be able to break a bond. And if we break a bond, we can make a rearrangement happen, right? So the point is then is that when it comes to temperature in a glass, when the temperature is high, the grains have a lot of vibrational energy, and that allows them to explore and move around a bunch of different configurations. And if they happen to get locked in a configuration that's bonded, if the temperature's high, they're likely to eventually get kicked out of it, right? And this is the idea that I talked about earlier, that if we imagine that the energy landscape is something like this disordered material, and I'm like a boat sitting here on the surface that as I bring down temperature, it's like I'm bringing down this surface level, right? So here it's easier for me to move around. When the water level gets lowered to here, I might get stuck here, but with enough energy occasionally, I might, if the boat gets a lot of inertia, it might slide over that shoal and make it into the next one. But as the level gets lower, it becomes inaccessible for me to jump from one to another. And now I'm locked in this state, and now I'm rigid, right? So in the case of the glass, it's the easiest to understand. The way to think about these other things then is that they are, volume fraction and stress are somehow constraining the motion of the particles, right? So when you think about like, you know, increasing the packing fraction, the volume fraction in a suspension, right? When it's dilute, it's like this boat up here. It can move anywhere it wants to, right? But as I increase the packing fraction, I'm essentially constraining motion. And I'm now, increasing the packing fraction is like bringing this water level down and down, where I have a configuration that is locally locked up, and but I'm in a regime where I'm more likely to get locked up, right? And so I'm not explaining it super well, but that's the best I can come up with. And then similarly with stress. Stress is maybe easier. If I think about stress, when I drive the system hard, that's like dumping energy into it with temperature, right? So in a granular material, when I stress it hard, it flows. And I know that the grains bang into each other and dissipate energy, but I'm dumping so much energy in that it's larger than the dissipation that's coming from the collisions, and it can flow. And as I lower the stress, basically the grains need energy. If they want to keep moving, when they bang or rub into each other, they dissipate energy. And if they want to keep moving, you have to dump energy in, because they're always dissipating it as they bang and rub and collide with each other. And so as you lower the stress, it's stress, not energy, but it's like you're just diminishing the energy that you're pouring into the system. And so the grains will get locked in some configuration, but you're not likely to knock them out of it anymore, right? And so that's the way that I think about it. But there's not a deeper answer. What I mean is the deeper answer of why is the project of the jamming phase diagram, right? It's like the project that a lot of soft matter is on. So from a like first principles perspective, we don't have a super deep answer yet. Yeah. Shameless plug though is that it feels kind of like random walkie or percolation stuff, doesn't it? Right? Like, why are these all so similar? I came up with a very generic answer about these factors constraining degrees of freedom or constraining motion, because the feeling is it has to be something super generic, right? In order for these things to be similar, despite the fact that the microscopic physics are so different, it has to be some very, very generic thing that doesn't invoke system-specific physics.
So you talk about like percolation class problems, like
Yeah.
problems that look like percolation.
Yeah.
Is randomness and connectivity like a sufficient condition for a funky class this way? Like for example, I don't know, a bad example, but I'll say it anyway. If you had an electrodeposition branching thingamabob, then you apply a magnetic field and now it's leaning this one way, can you still extract like
So the question is about like, you know, is how general, maybe I would rephrase as how general is the percolation universality class. So things change with dimension, which is important. And, you know, I always just draw things in the minimum number of dimensions on the board. But directedness changes stuff. So there's isotropic percolation, so where things are equally likely to happen in all directions. And then directed percolation is a subclass, and it's distinct from isotropic percolation. So the examples that I gave were actually really directed percolation ones, like the pipe flow is moving in one direction, right? And what that means then, and I'm going to talk about this a little bit next time, and the details do matter. Like I'm going to talk about that generically, that critical point, like we can say that percolation happens, but at what density of things is very system specific. But generally, people do make a distinction between isotropic percolation and directed percolation. And this is where things get slippery, is where the boundaries are, right? Because there's a lot of isotropic percolation problems, and they're not perfectly isotropic, but they're isotropic enough that things turn out quantitatively the same. And then we know that directed percolation, where things have a strong tendency to go in one direction, we know that there's a directed percolation class that has quantitative scalings that are different from isotropic percolation. And we know that a lot of systems fall in that class without being super specific about how directed they are. But there must be a boundary where things are isotropic enough that you're in the one class, or they're directed enough that you're in the other class. And it's not clear how to figure out where that boundary is. And so it's one of the things about universality and universality classes is we tend to say there's a universality class. The universality class is defined by all these systems have quantitatively similar behavior despite differences in their microscopic physics because they are qualitatively similar in some way, right? And we can come up with precise scalings for how things should behave in this universality class. But if you say, can I precisely write down where the boundaries are? No. Almost never, right? So there's this interesting thing that we can say, things are universal in that room. And then you say, how big is that room? And I'm like, well, it's big. But someone's like, yeah, but I need to know where the wall is because I'm going to be doing construction next door. And you're like, ooh, don't ask me to tell you exactly where the wall is. Do you know what I mean? And so, yes, directedness does matter, for example. And you'll get different quantitative results and different scalings. But where you transition from one to the other is less clear.
Yeah. So there's like a lot of thresholds in the world, right?
Sure are.
Can we put all of them into classes like these? Like, if I have a piece of paper and I pull on it, there's a threshold at which it will break. Does this have some sort of like class that it belongs to?
You mean for the condition of tearing your piece of paper, for example?
In general, right? Like all these systems you brought up are interesting ones, but
yeah.
I'm sure that there are uninteresting systems that are also like, you could say that they have a critical threshold.
Yeah, that's right. And so an example, like a good example, for example, paper is a good one. Breaking is another one, right? So what's important here is some amount of randomness. And it seems like in almost, I'm sure there are examples someone could come up with, but all the examples I can think of universal behaviors, universality classes, power law scalings, are all systems with a high degree of randomness. And so even this like percolation crack thing, so you could have a totally homogeneous solid material and you could stress it in a super controlled way. And you will basically make one crack that you can make it sure that it goes in one direction, and the crack will rip through the material and split it in half, right? And in that situation, you're like, well, sure. I mean, it broke when the crack percolated, but there was no network of anything. There was one crack that grew deterministically in one direction, and that clearly doesn't look the same as all these random cracks growing in a random network, right? And so there are situations, and this is also true if I go all the way back to creep in crystalline materials, right? So when I think about crystalline materials or phase transitions in crystal materials, right? So they're first order phase transitions, like the viscosity abruptly changes. And it abruptly changes because there's just this there's this abrupt shift from one configuration state of the molecules or whatever to another configuration state of the molecules, right? And there's nothing in between. Now, there is a theory of first order phase transitions, of course, that predicts like freezing fronts and all this kind of thing. It is a theory that is very deterministic. And it is a theory, though, where all of the details about the magnitude of the viscosity change and all that are system specific, right? Another example that I'll give is that I know I'll talk about this a little bit next time, and the details do matter. But another example that's nice in thinking about materials is a critical strain that materials fail at, okay? So if you take a crystal of quartz and you say, how much relative deformation do I need to put on it before it falls apart, right? You can come up with a pretty specific value. And if you choose to do that with a chunk of diamond or a chunk of olivine or a chunk of some other crystal, each of them will have a different amount of deformation before it falls apart, okay? And it is all related to its crystal structure and how many holes in that crystal structure that there are and how those holes move about. Which means that there's a theory for how they yield, but there's no common like stress or strain that they fall apart. Each one is different for each material. But for some reason, when we look at amorphous solids, so these can be sand, it can be polymer gels, colloidal gels, metallic glasses, foams, pretty much any emulsions, they yield at 3% strain. We don't know why. But what we know is that, now the stress that they yield at is very, very different. But somehow, all these systems with very different interparticle interactions and all this kind of stuff have the same amount of deformation that they can accommodate before they fall apart. So that's an example of like, there's crystalline materials and they do not have a universal strain. And then there's all of these weird amorphous solids that are wildly different from each other, but they have this universal characteristic to them. So there's something about this high degree of randomness or disorder that collapses all of their variation in their behavior and makes them like kind of simple in this way. You know, which is cool and mysterious. Yeah.